All right, section 9.2, we're going to start talking about multi-stage experiments. Now, we could have started what I'm about to show you in 9.1. In fact, I drew something on the board it was your group, Shelby, last time, where I said, I haven't talked about tree diagrams yet. Tree diagrams are very first presented in 9.1, but they don't really get used very much in 9.1. So 9.2 is where we actually see them used quite a bit. A tree diagram is a sample space model where each outcome is designated by a tree branch. You may have seen a tree diagram before. You may not have. You can work with probability and never talk about tree diagrams. In fact, when I teach contemporary math and I talk about probability, I don't use tree diagrams because their book doesn't use them at all. But they're a great visual, and they're excellent when you're working with younger students because of that, for that visual. So there are two different kinds of experiments. One would be called a one-stage experiment, and the other one would be called a two-stage experiment. So I'm going to use that example we did last time where we had our die that we rolled. So if we were drawing a one-stage experiment for our die, what we do is we start with a node or a dot, all right? And we draw all the branches off of that dot for each of the outcomes that could have occurred. So we could have gotten a number 1, we could have drawn a 2, or a 3, a 4, a 5, and I'm totally running out of space at 6. Usually you see them drawn straight out to the sides, but sometimes you'll see them drawn as well like this. That would fit my space better, wouldn't it? Sometimes you'll see them drawn sort of from a top-down perspective. They almost look like roots. They don't really look like trees if you draw them that way, but that's okay. This is a one-stage experiment. And we can actually, on each of the branches, we can write the probability. So what's the probability of me rolling 1? 1/6. What's the probability that I roll a 2? 1/6. A 3. 1/6, and so forth. These are all 1/6s. 1/6. Now, depending on what we were working with, they may not all have to be the same. They certainly wouldn't have to be the same. A two-stage experiment means that we do an experiment twice. That's all it is. We do it in 2 steps. So for instance, if we wanted to roll the die twice, or equivalently if we were rolling 2 die, we could do a two-stage experiment with this, and it would actually look like something like this. And I'm not going to draw, so here's my first 6 nodes. 1, 2, 3, 4, 5, and 6. And then what we would do afterwards is that off of each of these branches, we would draw 6 more branches. Okay? Most of the ones you work with are not going to have 6 outcomes possible, so your trees are not going to get this crazy. All right, so pretend there's all those 6. And they've got to be on every branch, so each of the numbers has a branch beside it. So if I wanted to use, let me actually delete this. If I wanted to use my picture where it's drawn from the top down above, can you imagine drawing out 6 more of these over here? Okay, does everybody get the idea, or do you need to keep drawing? Are we good? And we would write the number at the end of them, 1, 2, 3, 4, 5, 6, all the way across. Okay, so that's what a two-stage experiment tree diagram would look like. A few features about these trees. Let me show you on the next page. There is a multiplication rule for tree diagrams. For all multi-stage experiments, the probability of an outcome along any of the paths of a diagram is equal to the product of the probabilities. So let me go back to the picture that I just had so that I can talk about what that means. If I wanted to know the probability of rolling a 1 and then a 1, I could actually talk about that based on the 2 probabilities of these branches. This is a 1/6 probability. There's a 1/6 probability the second time that I roll a 1. And I could talk about this 1/6 times 1/6, which is 1/36. So there's a 1 out of 36 chance that I roll a 1 twice when I roll a die, a single die. And we could do this along any of the branches that we'd want to. That's what the multiplication rule is that it's talking about on the next slide. So are we clear on what that means? All right, so this note in the middle of the page, it's actually red on my screen. It's not very bright, so you can't see it too well. But highlight it, circle it, star it, something. This is important, important. I want to see tree diagrams in all your work. All of it. Because at the level of age of kids that you would be working with for probabilities, that's how they do the problems. They would use tree diagrams. So I want to make sure that you understand how tree diagrams work and can use them appropriately. That's how I want you to actually find these probabilities. Not because it's the only way to do it, but because that's the way you'd be teaching it if you were teaching it. Does that make sense? Okay, so expect to see tree diagrams even though the book's not going to say draw a tree diagram. Independent events. I mentioned this before, didn't I, Lydia? When you were talking about the flips being different, they don't affect one another. Independent events are events that have no effect on one another. Okay? They have no effect on the outcome of another event. That's what happens when I roll that die, right? When I roll the die, there is no effect on my second roll based on what the first roll was. It's the same thing if it's an equally weighted die. Last one on here, the theorem 9.7. For any independent events, E1 and E2, the probability of rolling or of getting event 1 and event 2 to both happen is the probability of event 1 times the probability of event 2. And that's actually just an application or maybe a stronger statement of the multiplication tree rule at the top. Anything along the branch, the way I get the whole branch to happen is I multiply the two pieces of the branch, or multiply the two branches' probabilities together. All right, so we're going to do an example. We're going to draw lots of tree diagrams today. I will show you one case where a tree diagram maybe isn't the most helpful, but other work that's visual will be. So there are a couple of examples of that happening in your notes, and you can certainly use that fact in your homework as well. Here's a good one. So this one says, an executive committee consists of 10 members, 4 women, 6 men. 3 of them are going to go to Hawaii. And what we're going to try and find out is the probability that all 3 of the people going are women. Okay, is everybody with me? So if you imagine the picture here, you've got 10 people, and they're sort of either lined up randomly, or maybe a better picture would be they've got their names in a hat, right? Randomly in a hat. And so the executive of the company reaches in, and he draws one name out of the hat. Okay, can you picture that? All right. So the only concern that we have is whether or not the drawn name is a male or a female. Agreed? Okay, so we reach in, we draw one name out. When we draw out the one name, it's going to have somebody's name on it, and they are a male or a female. It's one or the other. So what is the likelihood that that person that we draw out is a male? 6 out of 10. Okay, Kinsey, where did the 6 out of 10 come from? Right. So there are 6 men's names in that basket of names or whatever, and there are 10 people total. So what's the likelihood then that they'll pull out a woman's name? 4 out of 10. But this would be where I would stop if we were only sending one person to Hawaii, right? Only rolling the one die. This is a one-stage experiment. But how many people am I supposed to send to Hawaii? 3. So we're going to take this diagram, and after we draw person number 1's name, we draw a second person. And when we draw that second person's name, again, they are either male or female. But it matters whose name was drawn to begin with. This is not like my coin, is it? Because you see, when I pull person number 1's name out, I don't put their name back in. They're already going to Hawaii. Okay, so if I drew a male's name out the first time, then how many male names are still in the basket? 5. So that's what the first branch is. The first branch says I drew a man's name out. So what happens? How likely am I to draw a male's name on the second draw if I already drew one male's name out? 5. Out of how many names? 9. Because there's only 9 names in the basket. I don't care whether they're males or females at this point, but there are 9 names left. How likely am I to draw a female name? 4 out of 9. Now, on this second branch down here at the bottom, they're going to be out of 9 as well. But the numbers are different. Because down on this branch, what we're saying is we drew a female's name out the first time. So if I drew a female's name out the first time, and I draw a second draw, how many men are still in the basket? 6. And how many women are still in the basket? 3. So we've got 6 out of 9 here and 3 out of 9 here. But that's only 2 people going to Hawaii, right? How many people are supposed to go to Hawaii? 3. Which means I do another set of branches off of each of these. And each time, I care only in this particular situation whether the person is male or female. Okay, so how many names total are in the basket right now? 8, because I've already drawn 2 out. So all of these have a denominator of 8. Numerators are going to change a little bit around, but they all have denominators of 8. Okay, so it matters which branch you're on. So let's do the very top branch. The very top branch says I drew a male and I drew another male, so how many males are in the basket? 4. How many females are in the basket? 4. There's still 4 in there. None of them got drawn if we're along the top branch. All right, so now we're going to be along sort of one of the middle branches. This middle branch where I went from male and then I drew a female. So then, how many males are left? There are 5 males left. How many females are left? 3, because I drew 1 male and 1 female already. This middle branch down here is very much the same branch. It's just that I drew the male and the female in a different order, right? I drew a female first here, and then I drew a male. So how many males are left? 5. And how many females? 3. Why? Because I drew 1 female, 1 male. It's okay. There's lots of numbers going on the slide. There are. Last branch down here, I've drawn 2 females, right? So on this branch, how many males are left? 6. And how many females? 2. Okay. Probably should note for you that we've not answered any question yet. You realize that? Sometimes people get so excited about the tree diagram, the beautiful tree diagram, they never answer the question.
I think this would not help me. This would just confuse me.
It depends on who you're working with, Kinsey. So to me, absolutely love tree diagrams. Absolutely love them. I'm a visual person, though. I see this, and it looks like perfect sense to me. Yes, Kelly?
This is just a preference question. Do you prefer us to do our tree diagrams like that, or can we do it like where it's going down?
Like this?
Yeah.
It doesn't matter to me.
Okay.
Either way's fine. It's a little bit easier to manage space if you go down on your paper like that, so some people like to do it that way. Yeah, either way's fine, though. Okay, we're about to answer the question, though, all right? We're going to use this diagram to answer our question. Our question asks, what's the probability that all 3 selected are women? So do you see the branch that answers that question? Yeah, it's this one down here, right? So what would I find? How would I use that information to find the probability that all of the women, all the people selected are women? Yes, I would multiply those 3 fractions together. So it would take 4/10 times 3/9 times 2/8. And what would you get, or what do you get? I didn't even write the answer down, actually, so you're going to have to tell me. We can reduce some of it if you'd like. You want to reduce some of it before we even multiply? How about that 4 becomes a 2 and the 10 becomes a 5? The 3 can become a 1 and the 9 become a 3. We can reduce those. That's an awful 3. Try that again. The 2 can become a 1 and the 8 can become a 4. Excuse me. And this 2 and this 4 can reduce to 2 and 1 if you want. I would get a 1 out of 5 times 3 times 2. What is that? 30. There's a 1 out of 30 chance of this happening. What is that in decimal form? What is it? 0.0. Let's give me a couple decimals more than that. 3 what? Oh, it's 0.3 repeating. They're repeating, so like this. Yeah. So 3 repeats. We've done repeating decimals. Let me write it that way for you. So if you wanted to sort of talk about this in terms of a percent, this would actually be a 3 1/3% chance. So is that really likely going to happen? Probably not going to happen, right? And even less specific if you actually talked about which particular females you wanted to go on the trip with you, because you might care. Just thinking, you know, out loud. We might care. So let me talk about this diagram just a little bit further, because I want you to see, it kind of feels like if that's the only question I'm asked, we did a lot of work to create the diagram, right? Often you'll have more than one question asked, though. What if instead they said, also, what is the probability that 2 women go on the trip? That's a much more difficult question And this diagram really helps with that. Because there are several branches that have 2 women on them, aren't there? All right, so let's take a look at them. Let's see. I've got this branch that's got 2 women, right? I've got this branch that has 2 women. And I know my diagram is looking awful now, but I've got some color, so at least that's something. I've got this branch that has 2 women. There are 3 different branches that have 2 women. Yes, Ashley?
How can you tell if there's 2 women or not?
Because I used M's and F's. F is female and M is male. The ones I circled are the only ones that have 2 females listed.
So you're saying on the bottom, since we started and we had 1 female, then we went to a female, then we went to a female, that was 3.
That's 3 females.
Oh, okay.
Yes.
Now I get it.
That's
Okay.
the 3 females that we selected
Got
out of the
it.
basket. So the blue ones that I circled are all the places where I have only 2 females, right? And you have to be careful, right? Does it say exactly 2 or at least 2? If it said at least 2, we'd include the last line as well, because that's 3. That's at least 2. If it said exactly 2, it'd be only the 3 blue ones. So what would we answer? Well, we'd multiply along the branches, just like we did on the last one. The difference is that at the end, we would add up those individual branches to get the final result. Okay? So let's multiply one of the branches so that you can see what it would be. So let's take this. Somebody do it in your calculator for me so that I'm not messing with fractions here. Let's do 6 over 10 times 4 over 9 times 3 over 8. It's 1/10. All right. Let's do the next one so that we can answer the question that I've sort of posed now. Do the 4 over 10 times the 6 over 9 times the 3 over 8. What do you get? Somebody get it? Oh, I hear lots of clicking. Somebody's getting it. What'd you get, Morgan? 1/10 again, right? Just for fun. Let's try it one more time. 4 over 10 times 3 over 9 times 6 over 8. So 1/10 again? All right.
I have a question.
Last one's not 1/10, obviously. Yeah.
Okay, so the last one you said at least 2 girls or whatever.
Yeah.
So would that work that you would just do, I know you just said this when I wasn't listening, so sorry.
It's okay.
Would you do like 4 over 10 times 3 over 9 and that would be it?
And times the 2 over 8. You would choose every branch that had at least 2 females on it. So it'd be the 3 blue branches that I've chosen plus the green or red branch rather that I choose to begin with.
Wouldn't that just be 1 over 30 again?
That one would be 1 over 30, yes.
For at least 2 girls?
Yes.
Why?
But then we would add those different 4 branches together to get the final result. The last one right there is the probability of having 3 women on the trip, correct? And then the 3 blue branches are the probabilities of having exactly 2 women on the trip.
Yes.
So if we want the probability of having at least 2 women, that would be 2 or more.
Yeah.
So we circle every branch that has 2 women or more, 3 women on the trip. And we take the result of multiplying all those branches together and we're going to add them. So if we wanted the probability, I'm out of space here pretty much, but let me write it over here. If we wanted the probability of having exactly 2 women on the trip, I'll use F since I used it before, 2 females on the trip, this would be the 1/10, 1/10, and 1/10, for a total of 3/10. That's 30% chance. There's a 30% chance at least 2 women are going on the trip. Okay? If I wanted the probability of at least 2 females, I'd have those same 1/10 that I just had, but I'd also have that 1/30th because that's the probability of having the 3 females. Because having 3 females is still having at least 2. It's not going to be as pretty of a number, right? I mean, I'm not going to be able to add these together quite so cleanly, but I can still add them together. 3, 6, 9. I think I'm going to end up with 10 over 30, so it's 1/3. It actually reduces really nicely, doesn't it? So there is a 1/3 chance when I reduce it that I will end up with at least 2 females going on the trip. I don't want to harp on this, but I know that some of the questions that are asked use the phrases at least and such like that in there. So you have to be aware of how the question's asked to know which branches apply. Okay, so if it says exactly 2 women, we got to circle the ones that only have 2 women. If it said at least 2 women, that means 2 or more. So all the branches that have 2 or more women in them. All right, let me do another one. Some of you guys are glazing over about tree diagrams. Let me do one that's not a tree diagram for you, okay? We're drawing things out of a box in this one. A box contains 5 slips of paper. The papers are numbered 4, 6, 7, 8, or 9. First player reaches in the box, pulls out 2 slips, adds them up. Okay? And we want to figure out whether we win or lose based on whether or not the sum is even or odd. So what I'd like to do is I'd like to write down all the different possible sums that we could reach in and pull out. Make sense? Okay. So one thing I could draw out is I could draw out a 4. We're going to make an organized list. So it's not going to look like a tree, but it's definitely going to have some order to it. I could draw out a 4 and a, what? 6. Or I could draw out a 4 and a 7. Or I could draw out a 4 and a 8. Or a 4 and a 9. And the reason I'm putting the plus between them is because the way I'm going to determine if I win is if the sum is even or odd. Okay? But maybe I don't draw a 4 at all. Maybe I draw out a 6, because I've written out every possible combination of drawing out a 4, right? Every way that I can draw a 4 and something else is included on this list already. So I don't need to list 4 anymore. So I could do a 6 and a, or a 6 and a, or a 6 and a 9. And now I have listed every possible way of having a 6, either in the list with the 4s already or in its own list. I don't need to list 6, 4, because it's already been listed. Okay, I'm not duplicating what's in my list. But maybe I don't draw out a 6. What if I start with a 7 and a 8, or a 7 and a 9, or the last option is 8 and 9. And because I'm drawing the 2 slips out at the same time, that's why I can't get duplicates. Like I can't get a 7 and a 7. Now if I put it back in and I tried to draw again, then I could have a 7 and a 7. That would be a different situation. So count up, how many different ways are there here of drawing 2 different digits? How many do I have up here? There are 10. There are 10 different, I'll call them draws. That's it. That's all there are. It may have felt like there should have been more or less, I don't know, but there are exactly 10 different ways that you could have drawn out numbers. It says if it's even, you win. If it's odd, you lose. So let's go through and find out the ones that are even. So somebody tell me what you get. Which ones are even?
4 plus 6. 4 plus 8.
6 plus 8. Okay, so how many odd ones are there? I mean, even ones are there, rather? 4 out of a 10 total, which means what's the probability that you win? Sorry, 2 out of 5. And if you want to turn it into a decimal, you could. This would actually be a 0.4 chance that you win. Most of the time your book's going to leave them in fractional form when they have that option, but if you want to change them into decimals, you could. Now we're going to make one slight change to the rules and see if it affects things enough that it matters. What's the probability player wins? I already wrote that on the next slide. I'm sorry. Probability that wins. I already wrote that. That was 1 out of, or 2 out of 5. It says, does the probability change if the 2 numbers are multiplied? Okay, so instead of having 4 plus 6, I have 4 times 6. 4 times 7, 4 times 8, and 4 times 9. 6 times 7, 6 times 8, and 6 times 9. 7 times 8, 7 times 9, and 8 times 9. I still have 10 possible combinations, right? 10 possible things that could happen. But which ones of these are even? And you should be able to tell without actually multiplying them. What about that first list? They're all even. How do you know? They're all multiplied by 4, and 4 is even, right? When you multiply something that's even, it gets you more even. Even, all the way. What about the second list? Yeah, all even. How about the third list? The top one is, but the second one's not. And how can you do that without actually even knowing multiplication tables on that? They're both odd. And when you multiply 2 odd numbers together, you can't introduce a power of 2 or a factor of 2. It's just not there. And then 8 times 9, same thing. We've got that 8 and the 9. So what's the likelihood of winning if the issue is about products instead of sums? 9 out of 10. This is how carnival games are done. This is how casino games are done, is using these probabilities. All right, let's take a look at another one. This one is a spinner problem. We have an experiment of spinning spinner X, that's this first spinner, I should label these, and spinner Y, that's the second spinner. And the first thing we're going to do is we're going to write down the sample space of what could happen. There's lots of ways we could write this down. We are going to write it in curly braces because that's how we list our sample spaces as a set. So we could spin the first spinner and get a what? A 1. We could get a 1 when we spin the first spinner. I'm going to write them as ordered pairs. And then I could spin the second spinner, spinner Y, after that, and I could get a 1. So I could have a 1 and a 1. Or I could spin the first spinner 1, and I could spin the second spinner and get a 2. Or I could spin the first spinner and get a 1, and the second spinner and get a 3. Now, I'm able to do what I'm doing because these are evenly divided circles. The first circle, you're equally likely to spin a 1 or a 2, right? It's that angle thing that we talked about on the previous problem. Over here, we're equally likely to get a 1, 2, or 3. So we don't have to actually worry about the probabilities individually because they're all equal. All right? All right, how about this? Maybe I don't get a 1. Maybe I get a 2. I could get a 2 and a 1, or a 2 and a 2, or a 2 and a 3. All right, everybody good? Okay, these are the different options of things that could happen. So we're going to find the probability then of spinning 2 even numbers. So looking at this list, how many are in the sample space? How big is the sample space? 6. Yeah. So the number of items in the sample space is 6. How many of them have 2 evens? Just 1. Which one? 2, 2. So there's a 1 out of 6 chance of spinning 2 even numbers when I do this spinning. How about spinning, okay, there's this phrase now, at least and exactly. At least 1, 2. What did you get? Somebody said it. 4 out of 6. So I include the 1, 2, I include the 2, 1, I include 2, 2, and I include 2, 3, because each of those have at least 1, 2 in them. So this is a 4 out of 6, which reduces to what? Good. And then how about exactly 1, 2? 3, 6. We do not get to include one of those numbers, do we? If we want exactly 1, 2, this list that says 2, 2 in it, that particular spin doesn't count. So it gets thrown out, and we only have a 1/2 probability of that happening. Okay, here's a fun one. I think the next time I teach this class, I'm going to have to change the problem to ripping holes in his jeans, because that's what my son does even more than he stains his clothes right now, is he rips holes in his jeans. Example number 4. When I purchase a new shirt for my son, there's a probability of 0.15 he will stain it the first time he wears the shirt. And if he goes to school, that percent has got to be higher, because then he eats at school. If the shirt is stained, there is a probability of 0.2 that I will not be able to get the stain out. What's the probability that my son's new shirt will be permanently stained the first time he wears it? All right, so here's the way the problem works. One of 2 things happens, and the order kind of matters. I mean, we can't even talk about getting the stain out if the stain's not there, right? So the first issue is that the shirt is either going to be worn and be stained or worn and not be stained. Does that make sense? So we're going to draw a tree diagram. You're going to like this one. There's only 2 branches. It's stained or it's not stained. So far, are we good with the tree diagram? How likely is it that the shirt's stained? 0.15. So then, how likely is it that he wears it and it's not stained? 0.85. So where in the world does 0.85 come from? Because it's not in the problem directly. It's subtracted from the number 1. And it's actually one of those probability rules, the last one, number 6, when we wrote them all down, that summary to the table that we very first started with today. It's 1 minus the 0.15. Okay, now there's another process here, right? The issue is after he comes home with the stained shirt, I got to try and clean it. But do I draw that branch on both of these branches? No. Why not? If it's not stained, I don't have to try and get a stain out. It doesn't exist. So this particular tree diagram only has another branch off of the stained part. So either when he stains it, it comes out, I'm able to remove it, or it stays in, permanently stained, and that means I can't ever sell it to another child again because they won't let me. All right, so what is the probability that it comes out? Is it? Right, so go back up to here with what the point 2 is. The point 2 is that I will not be able to get it out. So that's the stays in one. That's this point 2 down here. So the probability it comes out then is 0.8. All right, so the question that I'm actually asked to decipher based on this information is what is the probability that it will be permanently stained after the first time he wears it? Where in this diagram is that information? So you guys are sort of pointing at my board. I think this is where you're pointing. I hope so. Is that where you're pointing? Yeah. All right, so this is the probability that it's stained and that the stain is permanent. It stays in. So how can I find out the likelihood or the probability that that actually happens? You multiply 0.15 times 0.2 and we get 0.03, which is actually only a 3% chance. I'm quite certain that these were made up probabilities. There's no way that that's for real. Any questions on this one?